Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. Now, what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but a lot of the same principles apply over in the UK as well. Now, if you have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring that. And if you're watching this after the premiere, then just feel free to leave a comment underneath the video, and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on Diagnostics technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had a group of about 30 different franchisees I worked with, as well as the shops that they service, in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru, so I worked in a dealership, and over time, I guess, I just became that default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that had come into my bay. Then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So our topic at hand today is going to be misfire diagnosis, those pesky misfires. And there can be multiple reasons why I might have a misfire on a vehicle. Some are more common than others, and I've seen some really off the wall ones. So you never quite know what it's going to be, and you really don't want to just parts cannon the thing, right? Just throw a bunch of parts and hope that it'll solve the problem. You want to actually go through and figure out what the actual cause of the problem is. And there's multitude of tests that you can use, and I'm going to show a few of them in this class here. Because if we think about, we have 4 ingredients for combustion in an engine. So we have air, need fuel, need a combustion event, so spark or otherwise in a diesel, and then compression. All right, so air, fuel, and ignition source and compression. There we go. So we're going to talk through all 4 of those and ways that we can test different aspects of the air, fuel, combustion, and compression. First off, we'll start with oxygen sensors, because that can lead us down the road of here's where I might need to look, because they start telling the computer what's going on with the exhaust. They sense oxygen in the exhaust and tells the computer, here's how much oxygen is in there. It's rich or lean. Even goes all the way back to the 80s with the single wire sensors, unlike the old GMs and stuff. Up to nowadays, we have the 4-wire with the integrated heater and everything, and these are zirconia sensors, so these are used on a fair number of vehicles. I think they're less and less common as we go by, but some vehicles use both kinds. But we'll talk about the zirconia sensor first. So that is, it's got a cell with a zirconia membrane in it, and then it measures the exhaust gas on one side, and it has reference air from the outside on the other side of it. So if you look back here, you can kind of see where they're like crimped or whatever. If that gets bent and closed off, then it won't have the reference outside air, and then it won't work correctly. So we always got to make sure they're not damaged. Even if they only look slightly damaged, it could affect the operation of the sensor because it needs that reference air. So here's how much reference air is out there. Here's how much oxygen is in the air around me, and then how much is left over in the exhaust gas after combustion. So if it's too much, then it's lean. If it's too little, it's rich, right? And it produces its own voltage. So it generates a voltage based on how much oxygen is in the exhaust. Range is roughly 0.0 to 900 millivolts. Usually it's a little higher than maybe 100th of a volt or 100th of a millivolt, whatever. It's most accurate at 455 millivolts, which roughly translates to 14.7 to 1, which is where we want to be with our air-fuel ratio. And because of this, the ECM must switch back and forth from rich to lean to rich to lean to rich to lean, because it's going to bounce around. The voltage is going to bounce around. So as we said, an ideal air-fuel ratio is 14.7 units of air to 1 unit of gasoline. That's, of course, at sea level. It may vary depending on your altitude, but for the most part. And you see that's in a very narrow band of voltage there. We go from 14.5 to 15.4 over just 1/10 of a volt. So that's roughly 455 millivolts. And it's positioned between a narrow band of voltage, which may be why you may have heard a zirconia sensor referred to as a narrow band oxygen sensor. That is why. And then if you were to look at it with a lab scope, you're going to see the voltage go up and down and up and down. It goes from rich to lean to rich to lean to rich to lean to rich to lean, back and forth as it cycles. And that's if it's in the front. If it's in the rear, it might be a different story. But in the front, it cycles back and forth, rich to lean, and that affects how the vehicle runs. Now, AF sensors have come on the scene in the last, better part of more than a decade, probably 20 years. But they work different than a zirconia sensor. It's actually two zirconia sensors put together, and it doesn't look a lot different than those zirconia sensors, but here we are. So it is two zirconia membranes. There's one over here and one over there. This one's the pumping circuit, and this one is the measuring circuit. We still have the reference air from the outside. We still have our exhaust gas over here. What this pumping cell does is varying the current moves oxygen ions in and out of this chamber here. Now this chamber wants to be at a lambda of 1. So a lambda of 1 would be 14.7 and 1 are stoichiometric. So it's moving oxygen in and out of here to keep that at stoichiometric. So this should be putting out 0.455 volts regardless of what's going on. And it changes the current in and out to keep that voltage at 0.455 volts. So it's a zirconia sensor with some extra accessories on the side. So it's two cells mated together in a planar form. So in a plane, so like think about plywood, right? Just plies of plywood. Use an entirely different operating strategy than a conventional zirconia sensor though. Like I said, one cell is used to measure oxygen in the exhaust stream, and the other cell is supplied with a very small electric current from the PCM capable of moving oxygen ions in or out depending on the current. Achieves a stoichiometric ratio between both cells, known as a pumping cell. Also operates at about double what you're going to see on a zirconia sensor, so about 1200 degrees versus like 640 on a zirconia sensor. And that's Fahrenheit, of course. But it's going to move those ions back and forth. So this used to animate, but you could see it kind of going back and forth. And based on the current, the computer does the calculation as to how many volts that actually applies to. So the PCM monitors the varying current. The PCM converts that current into a voltage value PID. So actually, if you're checking the PID data, this is really the only way you can see how it is working. Best way to test a sensor signals by monitoring the voltage PID. It's possible to monitor the AFR sensor varying current, but the changes are very small, low milliamp range, and difficult to monitor. You're probably not going to pick it up with a regular low amps probe. You probably need a microamps probe, which can tend to be difficult to come by because there's not a ton of them out there and they're fairly pricey for what they are. So if we can see, 0.66 is what your normalized OBD2 voltage would be, and that converts to stoichiometric there, and it goes from to 0.48 and then the 0.8. So you would look at the voltage PID and see roughly where you're at. So if you're at 0.66, then you would know you're at stoichiometric. And then there's just a little chart there. So whether it's rich or lean, rich will give you a negative current flow, lean will give you a positive current flow. Positive flow lowers the resistance and increases the current, thus increases the voltage. And then it works the opposite of how our zirconia oxygen sensor asks. So when the fuel mixture becomes richer, the voltage should decrease on an AF sensor, and the voltage is going to increase on the zirconia sensor. So they work opposite of each other. We'll see a good example of that in a little bit. Under lean conditions, the other way. So AF volts go up, O2 volts go, or zirconia volts go down. Which leads us into fuel trims. We talked about rich and lean just there. Well, that's what fuel trim does. So it makes it more rich or more lean in the mixture in order to get us to our 14.701 stoichiometric air-fuel ratio. Fuel trim's a window that allows you to see what the computer is doing to control fuel delivery and determine how the PCM's adaptive strategy is operating. So in the quest to get to 14.701, the oxygen sensor, let's say it reads lean. Okay, so now it's lean. So what's that mean? It means I got too much oxygen, which means I need to add fuel to offset that. So now I add fuel, and I keep adding fuel, and I keep adding fuel, and then all of a sudden, oh, now we're too rich. Don't have enough oxygen. So then we got to pull the fuel away. So we do a negative fuel trim. And the negative fuel trim pulls away, pulls away, pulls away, pulls away, till we get to lean again, and so on and so forth. Remember how it went up and down? That almost looks like a sine wave. That is our voltage going up and down. All right, so That's how it kind of feeds it. The oxygen sensor feeds into the fuel trim strategy of the computer. If it reads lean, you get a positive. If it reads rich, you get a negative, which can help us in determining where the problem might be. So the oxygen sensor reads into short-term fuel trim, and then short-term fuel trim over time pulls into long-term fuel trim. So short-term fuel trim's correcting what's going on right now. And then depending on, maybe the short-term fuel trim stuck at like plus 10% for a while, it'll then make the long-term fuel trim go up accordingly, and then it'll work off of that. So it's like they call it like block learning. So after a while, it'll move up, and then it just moves up, and then that's normal, and then it adjusts off that, and so on and so forth. So we'll be able to tell, looking at the fuel trim numbers, what's wrong, whether or not we have a problem going on there. So we're going to do a little case study here real quick. So create a vacuum leak. Just took the brake booster hose, cracked it off my intake. Observe oxygen sensors in relationship and comparison to fuel trim, and then repair the vacuum leak and see what happens. So here's an example here. Normal running, normal idle. The rear O2 sensor behind the cat is reading rich because all the oxygen got used up in the catalyst. And then air fuel ratio sensor, which is in front, that's trying to get around 1 because 1 is stoichiometric. Right? You might have heard it called the lambda sensor too. That's the same basic gist as it tries to stay near 1. Now this is on a Subaru. So on Subaru, they do things a little bit differently, at least on the OEM side of the computer. So short-term fuel trim is called air fuel correction, and long-term fuel trim is called air fuel learning. If you think about it, it makes logical sense because it's correcting in the short term, just for vehicle operating at the time. And then that feeds into the long term, which is learning how the correction is operating, learning how the vehicle is operating. So it makes sense, but it makes sense to no other manufacturer in the world. They all call long-term and short-term fuel trim. And actually, if you go into the OBD2 side, it's the same thing on a Subaru too. But right here, you can see where I kind of started cracking it open. The air fuel sensor went up a little bit. And then short trim went up a little bit. So 2, 3, 4-ish right there. And then as you can see, the long-term fuel trim is kind of trailing that, but it does trail it. And then we're opening up a little bit more. And then we finally open it up as much as we could without the engine stalling. And it went up to 35% positive correction. So that was a huge vacuum leak. The thing was barely staying running. I could barely keep it idling. But 30 plus 35%, and you see air fuel long-term went up to 6 during that time, and then it actually went up to 7 after we fixed the leak. You can see exactly where we fixed the leak because the front sensor went full rich, and then the rear sensor ended up going full rich too. Notice how the rear sensor took a little bit longer than the front sensor because there's a distance to cover, right? Front to rear, in front of the cat to behind the cat. It's a bit of a distance depending on the vehicle. So you can see where it drops off there, and then it makes the adjustment there. And as soon as that drops off, my short-term fuel trim drops off the cliff as well, and it goes down to like -4 was the lowest right there. So we're at -4. Whereas the long-term fuel trim is still at 7, +7. And it takes a little while for it to recover back to where it needed to be. You can see the short-term fuel trim recovered back pretty nicely, 4, 3, 2, 1, 0. So I was running roughly 0 there. Air fuel ratio sensor was running roughly 1 at that point. And then my rear oxygen sensor. Everything had kind of adjusted back to normal except for the long-term fuel trim at that point. So I just think that's kind of interesting. You can definitely see it in the data and see how it reacts. So a good rule of thumb is look at your long-term and short-term fuel trim. Long-term fuel trim is going to be more, hey, has this been going on for a while? Short-term fuel trim is, well, I don't think that's been going on for very long, but let's see how the engine's running right now. You might take a look at freeze frame data on a code or something like that and be able to see that as well. Actually, you would be able to see it, but might not necessarily tell you anything unless it's been going on for a while. It's in a long-term fuel trim. But plus or minus 5%, that's normal. Going in either direction, that's just normal fuel control. Going to have a warning when you get 6% to about 19% plus or minus. Rule of thumb that we were always told is anything double digits, start looking at stuff because there's a problem. And then if you get over 20%, you're going to get a check engine light. Now, you might get a check engine light earlier than that, but definitely over 20%, you should have a check engine light due to OBD2 emission standards. Probably wouldn't get to that before some sort of problem was noticed by the customer, a drivability problem or something like that. So always observe that. And then here's just a quick table for that. So if we're reading normal, stoichiometric, no fuel trim either way, it's going to pulse the injector as it's supposed to. If we have lean condition in there, low voltage on a zirconia sensor, it's going to go up to 100%, probably never get up to 100%, but it's going to go double digits either way, or double digits positive, and that will increase the pulse width and add fuel. Versus if we have a rich condition, it's going to command lean, so it can go negative, and then it will decrease the pulse width by subtracting fuel. So it's got to think, if it's rich, it's going to want a lean, it's going to want to pull fuel. So if it's rich, it's going to be a negative fuel trim. If it's lean, it's going to be a positive fuel trim. Correct. And that leads me to fuel injectors. We can check fuel injectors in 3 ways. We can go electrically, which is going to verify the circuit integrity, verify the component is operating, verify that the driver is working in the computer. Mechanically, we can view the current flow to verify mechanical motion. We can actually see the pintle move. And then hydraulically, we can look at the pressure. So we can look at the pressure change or drop and verify the state of flow in there. And it looks something like this if I do all 3 on the screen at the same time. So yellow is electrically, verifying the circuit's okay. Green is current, verifying that it's moving. And then the blue is the pressure. Not a huge drop. We'll talk more about that in a little bit, but the spike is what we want to look at. So here's a standard gasoline injector, a little top feed, constant power from the battery, or a fuse, I guess, or a relay. And then it is grounded by the PCM, controls the ground side. So it should have constant power here. And we can see there's my voltage. It's about 14 volts. So the vehicle has to be running, obviously, otherwise the fuel injector is not going to fire. What happens when we ground it, though, is we're going to power up these coils here. It makes an electromagnet, pulls that pintle off the seat, and it'll start spraying fuel out the bottom. So we ground it, turn it on, and then it starts spraying the fuel. Once it's done spraying the fuel, I just said these are coils in here, right? It's a coil of wire. When any coil is having electricity fed into it, it is going to store that electricity. Works on the same principle as an ignition coil. We'll talk about in a little bit. But it's going to store all that electricity, and when that ground goes away, all that electricity needs to go somewhere, all that voltage needs to go somewhere. So it gets induced back into the line. So that's why we get the kick at the end. So that's when it releases. And then this little bump right here is actually the point where that pintle snaps shut back on the seat. You get a little extra kick right there too. And then it goes back to 14, and then when it opens again, it does it again. So that's voltage. Current's going to be the same deal. Current's going to rise. We want to see it in a nice smooth ramp like that. In this case, we have a nice dip right there, a nice pronounced dip. So that dip is the point where that pintle actually leaves the seat and starts spraying fuel. So by seeing that dip, I can verify that, yes, that injector opened. Now, if I'm looking at a single injector, I want to keep an eye on that. If it opens roughly the same place every time, I know we're okay mechanically, internally. If it opens here, then opens there, then opens, it's just kind of willy-nilly and random along that ramp. You may have some mechanical issues in there. Probably a spring went bad. But that indicates that it has opened. And then, of course, when the voltage goes away, the current goes with it. So I have nothing left and no more current flow, and it's closed. Then we have pressure. So once it opens, the pressure is going to drop. In this case, it didn't drop by much. It went from 35 to like maybe 32 PSI. But what I found interesting was when the injector closed, we had a spike. So all that fuel is flowing into the injector, and then all of a sudden it has nowhere else to go, but it's still flowing in there due to the pressure. So now the door is slammed, so everything just kind of runs in the door and backs up. So it gets put back into the system, and then it gradually just recovers over here. In just a couple milliseconds it recovers. But I thought that was unique where you can see that. Okay, coils. So we covered air and fuel. Now we're worrying about combustion. So ignition coil. So ignition coil works on the principle of mutual induction. So there's a transfer of energy from one coil to another when they're placed in proximity to each other. There's going to be one coil connected to a voltage source, the primary winding. And a secondary coil connected to another circuit is the secondary winding. Also note that they share a common conductor in the middle. Usually it's an iron core, and usually the windings are made out of copper. So in this case, we have 10 turns of copper wire on this side, and we have 1,000 turns of copper wire on this side. That's 101. 100 times 10 is 1,000. We have 14 volts and 14 amps being fed through here, so that's 196 watts available energy. It's going to build up the magnetic field there. When that magnetic field collapses after the voltage stopped being applied, it will then transfer that energy over. 196 watts transferred over straight away. The voltage steps up by a factor of 100, and the amperage goes down by a factor of 100. So it's 14 divided by 100 is 14 hundredths of an amp, and then 1400 volts. In the case of a vehicle, it'd be like 30, 40,000 could be. But the current will still go down by a ton as well. That's why it hurts like heck, but you probably didn't die the last time you got struck by a coil. I know I didn't, but I didn't need coffee that morning either. So looks kind of like this. Found this little animation on the YouTube. So we're going to turn on the power, and that is dwell. That's going to start that primary coil charging up. So it's going to create a magnetic field. Then we're going to remove the electricity. That magnetic field then collapses, transfers all that energy over through electromagnetism, and then gives us enough voltage to cross the gap and make a spark. And the spark will look something like this. When we look at the secondary pattern, this is just a textbook drawing, right? So the dwell section where it starts charging that primary coil, you're going to see some coil oscillations in here as it's starting to fill the coil. And then it kind of levels off. And then when it's time to fire, we get the big firing line, which is the amount of voltage needed to cross the gap, because that requires the most voltage out of anything. So you'll see a tall firing line. And then the spark line requires much less voltage. Once the spark is established, it takes much less voltage to keep going. So we're going to see fairly level, should be. Should see a little bit of turbulence, should be fairly flat, like I said. And then depending on how efficient the coil is, we may see a few oscillations here, or we may see like barely any coil oscillations there. That's just the excess voltage dissipating out of the coil. And then it goes back to dwell again, back over here. So that is the life cycle of an ignition event from a textbook ignition pattern, you might say. So what can we test? Well, one of the easiest things to test is going to be the control signal. That's usually just a 5-volt square wave that tells the coil when to charge. So in this case, there's a coil control wire. And like I said, it's a 5-volt square wave. And it corresponds with dwell. So there's my dwell time right there. There's where it's charging up the primary coil. So once it sees 5 volts, charges the primary coil. Once the 5 volts goes away, it shuts off, and then it fires because it knows, well, it's time to stop charging. Collapse the magnetic field, fire that coil, secondary coil. So then I get my firing line there, my spark line there. Not many oscillations on that one. Can also check the primary voltage. This should fairly mirror the secondary voltage, and this might be the only test that you're able to do because some coils, the way they're constructed, they might not allow a very good secondary pattern. Maybe they do, maybe they don't. Depends on the vehicle. But in this case, we can see there's dwell. There's the firing line. Really not a lot of detail on the primary side in this case. I got better detail on the secondary side right there, right? So there's dwell. You can see how they line up, though. The firing lines line up. So at least you can tell if it's firing. Can't really tell the value of it, like the voltage. It could be, in this case, looks like it's about 6,000, 7,000 volts right there. In this case, it goes up to about 18 volts DC. So it's a reduced voltage version of this, and it doesn't give you as much detail as the secondary, but sometimes that's all we can do. Depends on the coil. And then in this case, I was able to use a secondary voltage pickup, so flag, and there's what our secondary voltage looks like on there. So there's dwell, comes up, fires. This, I think, is just kind of a factor of the probe itself. Because normally we're not going to have a negative firing voltage before a positive firing voltage, or positive instead of a negative, because technically that's inverted, but I digress there. And then there's your spark line right there. A little bit of turbulence, not a lot of oscillations, but that is a pretty darn good looking secondary voltage pattern. Then we can also check the current ramp on this. It should look very similar to our injector, except we won't have the pintle opening. So it should just be a nice smooth ramp up. And in this case, this is limited. So once it got to about 12 amps, that was it. Not going to add any more current in there. Other manufacturers, if they don't limit it, it'll just come up and down like a triangle. So either of those are acceptable. If it goes up very sharply and then over, that could indicate an issue inside the windings in there. It's got a lot of resistance to overcome before it starts flowing current through there. And then here it is overlaid with our secondary, right? So that is ignition. We did fuel, we did air, we did ignition. Now we can talk about compression. So there's two main tests that most people want to do or do when it comes to this type of thing. If they suspect it's a mechanical issue with the engine, you would want to do first a relative compression test to see relative to each other, how are these cylinders firing? Are they fairly even? Is one higher, is one lower? That'll give you an indication. And this is based on cranking over the engine with fuel cut to see how much current the starter draws and how much current it requires to turn the engine over. The more current required means I have more compression. The less current required would be lower compression. So it will show relatively to each other. Notice how the odd bank on this vehicle is lower than the other one. So what this ended up being, this was on a Jeep, and it was having a drivability problem. And what happened was it ended up with a clogged cap. And we'll show you another capture of that here in a minute too. But it had a large pressure pulse here, low vacuum pull. Wasn't able to get all of the exhaust out of the cylinder at the time, so it wasn't able to ingest as much air. So the compression was lower. So we can see that. Ended up, like I said, having a clogged cap because it couldn't get the exhaust out. And that would lead us to running compression. So if we see one of the cylinders, or I guess half the cylinders in that case, but if we see at least one of the cylinders is low, the odd man out, then I might want to do a running compression on it and see what's going on inside the cylinder. And if you can take a look at this pattern and analyze this pattern, you can see what's going on. Now, this is on a known good vehicle. So what happens is we're going to come in. This is going to be the compression stroke right here. So you can see the pressure is building in the cylinder. So imagine the piston coming up, right? It's compressing the air. Then we have our ignition event, usually at least a couple degrees before top dead center. There's top dead center. There's the maximum compression you're going to get because the ignition flame front takes a little while to go, so it's usually before. Then when it's coming back down, it's going to drop, of course, and all of the valves are closed, so I will end up in a vacuum. So down here we got vacuum. And then the exhaust valve will open, or valves will open, and then I can see, in this case, I got 3 pressure pulses from the other cylinders that it was able to kind of pick up on. This wants to stay below 0 because if you think about it, we're open to, the exhaust valves are open, that means we're technically open to the atmosphere. You calibrate the pressure transducer based on what atmosphere is where you are. So it says disconnect it from the vehicle, hold it, just hold it out in the air when you go to calibrate it, and that is 0 at that point. So relative to whatever your atmospheric pressure is, 14.701 at sea level, roughly. Anyways, then the intake valves would open. It would pull in the fuel and the air mixture. You're probably going to get a little bit of turbulence in there as well. And then the valves will all close, and then my compression event starts again, and then it starts all over again. Same. So that is a known good. That's what it should look like, roughly speaking. This vacuum pocket should roughly match this vacuum pocket. I'm going to show you another view here in a minute of this same vehicle, just with some more stuff added on, more channels added on. It's kind of interesting view. But first, the broken one. So here's a vehicle that was not able to build compression at all. I don't remember what the problem was. It wasn't a vehicle I worked on. But it was an associate worked on it. But wasn't building compression in that one cylinder. I don't know if the valves are busted or what. But not able to build any compression at all in that cylinder. And then, of course, to compare, because you want to compare, here's the cylinder right next to it. So that's a known good on this vehicle. And you can see it looks very much similar to the other one I showed you earlier. So that's pretty well textbook. And then here's the one off that Jeep that had an issue. So you can see it's over 0 psi, and it's actually increasing the further out it goes. So that just indicates it is not being able to expel those exhaust gases efficiently. Somebody made a pretty good comment that I saw today on the last time I did this video. Was think about it like a sink. If you got a slow drain, it's not going to be able to expel that water fast enough. If you start adding more water in there, like you're flowing the faucet, rinsing dishes, whatever, and you got a slow draining drain, eventually it's going to back up. Right? So you're going to see that eventually back up. So this vehicle had a bad cat on one side. Fix the cat, fix the problem. Our final slide for this part anyways is let's do it all together. So we'll look at air and fuel and ignition and compression. So compression goes up. There's my ignition event. So that's a current ramp. I had a current probe on the number 1 cylinder, or this cylinder. And I probably should have moved it up a little bit, but you see it's right about there. Oops. Too much. Right about there. So a few degrees before top dead center. And then top dead center happens, and then down it comes. And then there's my exhausts. And then interestingly enough, don't do this on a customer's car. I did this because it's on my own car, and I just wanted to see what happened. You shouldn't have fuel going into the cylinder when you're doing this test because you don't have ignition. Spark plugs out. So this is just washing down my cylinder. I didn't do it for very long. I just did it long enough to get a capture. But anyways, fuel injector sprays right before the intake valves open. So fuel injector sprays, air and fuel come in. There's my turbulence. And then it comes back. All the valves close. Then I get vacuum. And then I get compression. And then my spark occurs again, and so on and so forth. So that is all 4 of our pieces, all in combination. And I can tell that everything's working based on what I can see with the scope. It's pretty cool. All right, let's go live and look at a few other things we can look at between scanner and scope stuff. I got 4 different vehicles here we're going to look at. So first one's a Ford Escape. Now Ford, as a brand in our scan tools, has a few special tests that we can do. If we go to engine, functional tests, special functions. We have a relative compression test that's built in. That's from Ford. So what that does is it will rotate the engine. It'll crank the engine basically when you're in fuel cut. And then check the deviation from the mean cranking RPM of all cylinders. So it'll do a calculation and it'll tell you which one is lower. We also have a relative injector flow test. So that is it'll pulse the injectors and give us an answer there. So if we suspect it's an injector problem. Misfire monitor neutral profile correction. Anytime you do work on the PCM, internal engine repairs, or crank sensor or trigger replacement, you have to run that test. So that basically helps with the misfire monitor. And then also on most Fords now, might even be on most all Fords from a certain year, but this is the power balance test. So this has been refined over the years. It's much like the factory one, except we add in a couple other functions that aren't in the factory one. It's 2 separate tests combined together. But see how we have this graphical representation. Now, if it was running normally, it should all be roughly around the 0 mark. If I did see one way down here, then that means it is contributing negatively to how the vehicle is running. So that would be one I'd want to look at. That one's way high too. I think that's going to be much more rare that you're going to get a high one than a low one. A low one's usually it's got a dead hole. Also in here, you can turn off individual injectors. So let's say I wanted to turn off injector 1. Let's say it was running like garbage. Graph looks like this. And then I hit injector 1 and nothing changes. What's that indicate? If the injector I turned off and it's still running like garbage, then it's probably the injector because it wasn't doing anything for it. Now, if I turn the injector off and it runs worse, then I know the injector was doing something, right? So if I turn it off and there's no change, that's the first place I'm going to look at that injector. All right, that's everything on the scanner side of that. And then also in guided component tests, we have a multitude of tests in here. If you have a tool with the guided component tests, cam and crank, let's see, fuel system, right? Got fuel injector, fuel pressure test, fuel pump tests, ignition, of course, primary tests, secondary tests. Come in here. In this case, this one runs a multi-strike, so you'll see multi-strike possibly at idle. And then there's my pin assignments and all that. And then variable valve timing possibly could be an issue. If it's a timing related misfire, which if we get too far off, it may be. Oh, look at this 18 BMW. And what's that have in here? So we have, you might need to delete adaptation values. So that could be like your fuel trims and stuff. Injector coding if you have to replace the injector. Idle speed adjustment perhaps. Let's see. Vanos timing chain test. So that actually tells you whether it runs a test and tells you whether or not you have a stretched timing chain. Solenoid valves, Valvetronic limits. So that's for the valve system. So a couple things could be necessary for that. And then, of course, with data, they have cylinder status data in this case. Could also be called smooth running values on an older one. And then it just gives you your misfire counters. And then in guided component tests, BMW has a unique test in here where it's a compression test. Relative cranking compression using a low amp probe or using a secondary probe test leads. So you'd actually use your regular test leads that come with it, the yellow and black, clamp it onto a battery. And then due to the settings of this test, how it's set up, it will give you a relative compression based on the voltage drop when the starter cranks. So I think that's pretty cool. The peaks are all fairly even from min to max, and compression is good. If there's a weak cylinder, the peak will be much lower for that cylinder. Because since it's not drawing as much current, it won't draw as much voltage. And then, the regular stuff like ignition, fuel, the Vanos, VVTs, Valvetronics, that sort of thing. Could also be something in the wastegate because that would be airflow through the turbo. Jeep Renegade. CDJR is kind of unique in a couple ways in the scanner. It's a lot of ways in the scanner, technically, but some people get lost and don't know where this is. But if we go under system tests on the engine, and then there is a which cylinder is misfiring test. So that'll actually tell you your misfire counts, which is nice. And then, of course, there's going to be your engine tests under this. So things like the ignition coil, fuel system, mass airflow, even if it's an airflow problem or a leak, variable valve timing. So all those tests are readily available. And then last one, we're going to do this Hyundai Santa Fe because this has something unique in it too. So if we go into engine, it should be fairly straightforward, right? Resetting adaptives, perhaps. Functional tests. You can enable and disable your coils, enable and disable your injectors. That'll tell you, if I turn off the coil on that one cylinder and it doesn't get any better or it doesn't get worse, then I might know that that's a problem. Oxygen sensors as well, heaters, radiator shutters. But the real unique stuff is going to be in the guided component test. Hyundai and Kia have a cam crank relationship test in there. I don't know if this has made it to other vehicles, but you can verify the correct timing of the vehicle using that test. So it's going to just give you a pattern down here, and here's what it's supposed to look like. And you can do cam and crank together at the same time. So I always see on these LabScope and Diagnostics Facebook posts, like, hey, probably the most common question is, anybody got a known good cam crank for XYZ? And so we started adding cam crank correlation testing here, which I think is good. So that is misfire analysis, diagnosis, whatever you want to call it. And with that, that's our time here today. So make sure you tune in for new diagnostic content every week. We'll be premiering a new video every Wednesday at 7 p.m. UK time, so make sure to check it out here on our YouTube channel. Please make sure you also subscribe, thumbs up, and ring that little notification bell so you'll know anytime we post new content. With that, time for questions. Now, if you have any questions, once again, if you're watching this on the premiere, just leave it in the live chat and we'll do our best to answer those. Otherwise, leave a comment under the video and we'll get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've been giving you today. Hopefully we'll see you next week, and we'll see you on any of our other videos. Have a good week, have a good night, and take care.